There is no function where you have an exponent that grows at a slower rate than a log. If you have n to the 0.00000001, it still grows faster than the log function. Right? As long as the exponent is greater than 0. Alright, I think we're going to bypass the proof. Because I think it's really important that we understand the master theorem. The math behind that one, I can't give you the starting point. You start by using the relationship. If that was true, then the limit, I may end up working it out. So if that was true, or if there is a k greater than 0, then the limit as n approaches infinity of n to the k upon log n would have been equal to 0. Right? Now, we can actually find that limit by using a relationship they call L'Hopital's rule, which states that if you have a function and you differentiate the function, then the rate of change of the derivative is the same as the rate of change of the original function. So, if I differentiate it, I'll expect the same relationship to hold. So using L'Hopital's rule, I can find that limit by differentiating it. Of d by d so d by dn into the k upon d by dn of LGN. Now derivative with respect to n of log n is 1 upon n. Lim. You differentiate that, you end up with k times n to the k minus 1 and that works out to, remember this is n to the k minus 1 divided by 1 upon n, so this implying that function limit as n approaches infinity of k n to the k, which is, if n is approaching infinity, that limit will approach infinity. So we see the limit approach infinity. If that was true, the limit should have approached 0, so we know that's false. But the takeaway point is, as long as you have an exponent greater than 0, no exponent grows slower than a log. Of all of this was to make sure that we could actually solve those recurrence relations that we started working on yesterday. The structure that we looked at before involved drawing the recursion tree, and then we find the summation of all the overheads, and then simplify them mathematically. But as we saw, even though some trees may be simple and give us a pretty simple thing to work out when the overheads are summed, some trees can be really hairy. So it makes sense to try and simplify that process. Now, there are some guys, I don't remember exactly what the names are, but the name of the technique is a master theorem, who actually generated a certain class of recurrences where the general form of recurrence is T of n is equal to some constants n is equal 0 and a t to the n upon b plus f of n greater than 0.